Okay, dear student, welcome back. So probably this will be the last class of the quantum mechanics, and today we are going to look into some of the numerical problem, particularly on the eigenvalues and eigenfunctions. But before we move to the numerical problems on the eigenvalues and eigenfunctions, let us see some of the concluding part of the eigenvalues which we could not do in the previous class because of some technical glitches. So let's first try to understand that. So some facts about the eigenvalues. The critical analysis of the above facts lead to the following conclusions. So above fact does mean the previous class that we had done about the eigenvalues and eigenfunctions. We had got the derivations for your eigenvalues as well as the eigenfunctions in the one-dimensional potential box. So within that one-dimensional potential box, what we understood that we get a discrete eigen functions and eigenvalues. What it does exactly, it does mean that you had your infinitely high potential wall. So something like this, you had the infinitely high potential wall, and your energy value is starting from n equal to 1. So n equal to 1, then n equal to 2, like this, right? So these are your energy value. So this is for n equal to 2, this is for n equal to 1. So what it does mean, it is discrete and quantized, it is not continuous. So that is the meaning of this. So if this energy is discrete, naturally the wave associated with that is also discrete, right? Because we have the relation from the de Broglie relation between the energy and the wavelength. So from that we have already seen. So therefore the wave associated with them will also be discrete. So that we should understand. Now here we had also seen that energy is directly proportional to the square of the number of the energy states. So E is directly, or En we can say, is directly proportional to the square of n. Let us suppose in the first energy state we have got the energy is equal to E naught. So let us suppose in the first energy state, that is we are saying this is your E1. So E1, let us suppose your energy is equal to your E naught. So if I'm going from the E1 to E2, if I'm going from E1 to E2, then n square. So E2 will equal to 2 square. So E2 will equal to your 2 square. So 2 square is nothing, so 4. So it will equal to your 4 of E naught. So whatever you have the value in your first energy state, that has become 4 times. If I'm going to the third energy state, E3, then this will equal to n square, that is 3 square, and 3 square is nothing, so 9 into E naught. So this is how the energy is going to vary between the energy states, and this is why we are calling these are discrete. And of course if these are discrete, then therefore the wave function which is associated with them are also discrete, and that we should always try to remember it. All right, so now let's proceed further. Next we are saying from equation 10, where we had calculated the value of the energy, and there we have seen that the energy in any energy state is directly proportional to n square, which gives an infinite number of the discrete energy level. So in the potential well, you can have the infinite number of the energy states. There exists only one eigenfunction corresponding to each energy level. Thus, energy spectrum is non-degenerate. So naturally, we have seen for each of the energy state with the diagram I had shown you. For each of the energy state, we have got one particular value of the eigenfunctions, and this property is called a non-degenerate property, right? And we should try to remember this. Next we are saying the energy of the particle inside the box when it is in the ground state, that is ground state is nothing, is n equal to 1, and that is given by pi square h bar square upon 2ma, and then h bar is equal to h upon 2 pi, h bar is equal to h upon 2 pi. That value I have substituted and then slightly calculated. So then it can be given as h square upon 8ma square. This is the value of your ground energy state, that is the first energy state. E0 is not possible, that I have explained you in detail. So energy is going to start from the first quantum energy state, and where the minimum energy is not zero, right? You have a particular value of this, and what is that value? H, right? H is your Planck's constant at 8 m. M is the mass of the particle upon a square, that is the width of the box or you can say it's a vibrational state. How long it can vibrate the atoms. It's not that it is only moving in the potential box. Let us suppose here you have the atom, and atom can vibrate up to here. So this becomes its width. So this will become your A, right? So within this it is vibrating and it's a bonded. It's a right. So similar type of the case is there also. So in that case, we can say since all the atom will be vibrating even at the absolute zero, and this has been proven by the scattering experiment. Experimentally, it has been proven that you cannot have the zero energy of any atom, right? So if any atom don't have the zero energy, so naturally the zero energy is not possible, right? So this minimum value of the energy in the first energy state that we are getting is only called 0 point energy. So that we should always try to remember. We should not get confused that this value is 0. It is called 0 point energy, right? The fifth one, the spacing between the successive energy level is given as delta E is equal to En minus En1. That is what we have taken. Let us suppose we have taken n number of the energy state. So this is your any energy state En. This is your any energy state En, and just before that what will have En minus 1. So this energy state will be your En minus 1. So this difference will be called your delta E. So here you have got a energy, because as you know it's a discrete. So you have gap between these two energy state. So this is called your delta E. And that value, if I am going to substitute, that is what is the value I am going to substitute for nth. Here we can say pi square h bar square upon 2ma, and then n plus 1. This is for n equal to En, that is n square pi square h bar square upon 2ma square, and n minus 1 whole square pi square h bar square upon 2ma square. This value if I am going to substitute, and then if you are going to do a small calculation, then this is the value that I am going to get. This will be your value. So from what we are getting from this value is pi square h bar square upon 2m. This value is constant. Pi square h bar square upon 2m. This value is constant. 2n plus 1. N is your energy state, plus 1 upon a square. Now a can be your variable. So a is the width of the potential box. A is your width. So this width can be smaller width. This width can be larger width. But now you try to understand this. If this width is going to exceed and slowly it is going towards the infinity. So if this is increasing, naturally this value of the delta E is going to decrease. And if it is going to infinitely long, then this value will so small, then this value will become the continuous value. That is, the energy gap will not be there, so it will not remain discrete. So if the width of the box is very, very high, that is, the particle is exactly free to move wherever it want to go. There is no limit for this, right? Then in that case it is coming to your classical case, right? So this is what we exactly mean with this. All right, let's go to the next one. For the largest value of n, so whatever the largest value you take, and you take the ratio between that, that is En and En plus 1. But this should be the very high value. Nth value, it should not be 4th, 5th. It should be very large value. Let us suppose 100th energy state and 101th energy state. If you are going to take the ratio between that, then that is going to be nearly equal to 1. For the largest value of n, En upon En plus 1 is approximately equal to 1, thereby reaching to the classical limit. Alright, so these are some of the facts about the eigenvalues that we should conceptually we should understand, and accordingly we should deal with it. Right. So now let us start the numerical problem based on eigenvalues and eigenfunctions. So first I am taking some problem on the eigenvalues, and then we will be taking with the eigenfunctions. Right. So let us see the first problem. An electron is born in one-dimensional potential well of width 0.18 nanometer. So the width of the box is, that is, A value is 0.18 nanometer. Find the energy in electron volt in the second excited state. So try to understand this one problem. You should understand it clearly, and of course this problem is very, very easy. So what is given? An electron is born in one-dimensional potential well of width 0.18 nanometer. So width we have taken as A. So A is equal to 0.18 nanometer. So nanometer, so I have converted in terms of the meter. So 0.18 into 10 to the minus 9 meter. right? Okay, find the energy in of the second excited state. Second excited state does mean n equal to 3, because you are starting from 0 is your 1, 1, 2, 3, right? So 0 point energy you have already understood. So if I'm saying it's a second excited state, ground energy state will equal to E1, right? First excited state will be your E2, and the third excited state will be your E3, right? Second excited state will be your E3. So if you are being given second excited state, it does mean n equal to 3. If you are given fourth excited state, then n is equal to 5. If you are given second excited state, then n equal to 3. All right. So this you should clearly understand, because your ground energy state is first, right? E0 is not there. It is starting from E1. All right. The rest are your constant that we are going to use in the numerical problem. So now let's use the formula. What we have derived, that energy En, here we can say En, any nth energy state is equal to n square pi square h bar square upon 2ma square, where a is the width. H bar is equal to, we know, h upon 2 pi. So that value I have substituted in equation 1, and then this value of energy that is any energy state, nth energy state En equal to n square h square upon 8ma square. So this formula also you should remember, that is En is equal to n square h square upon 8ma square, so that you can directly substitute the value in calculating the eigenvalues, right? So now let's substitute the value. So what we can say, we have to find out the third excited state. So third excited state, nothing is a second excited state, so we are calling as E2, but the value of n is equal to 3, right? So what I have taken here, n, so n equal to, I have taken 3, so 3 square, right? H, the Planck's constant, 8, mass of the electron, into the width of the potential box. All those things we have calculated. So 1.675 into 10 to the minus 17 joules is your value. You divide it by 1.6 10 to the minus 19 coulomb. So this value will be coming equal to 104.7 electron volt. So this is one of your easiest problem. Let's move to the next. Now in this problem, calculate the energy in electron volt for the first excited state. So now here what we have, first excited state. So first excited state does mean n equal to 2 of an electron in an infinitely potential well of width 2 angstrom. So value of A is given. So what is given? N equal to 2, that is given. That is your first excited state, and the width of the potential box is given. The rest are your constant that we are going to use that. So what we have got from the previous problem, En equal to n square h square upon 8ma square, and here I am going to substitute all those values. So just I have substituted all those values. N equal to your 2, so 2 square will become your 4. All those values I have substituted. This is coming 6.038 into 10 to the minus 18 joule, and therefore if I am calculating, this is your value, 37.74 electron volt. All right, fine. Let us see the first excited state energy of an electron in an infinite well is 240 electron volt. Now you see the first excited states. For first excited state does mean n equal to 2, right? So first excited state of an electron in an infinite well is 240 electron volt. So you have electron in the first excited state, that is n equal to 2, and the energy of that electron is 240 electron volt. What will be its ground energy? What will be its ground energy when the width of the potential well is doubled? Now they are asking you, the electron is in the first excited state, right? And it has the energy of 240 electron volt. If that electron would have been in the first in the ground energy state, and the width would have been double, right, as it was there in the case of the first excited state, that is in the first excited state, let us suppose it was A, and then when the same electron has come to the ground energy state, but the width has got double, so its width has become 2A, right? So width has been double, then what will be the energy in the ground energy state? So this is what the problem has been asked. So what is the value that is given? So nothing is given. You have been given that in the first excited state, so naturally first excited state is equal to 2. there you have the energy of 240 electron volt, and you have to find out what is the energy in the ground energy state, that is E1. What is the energy in your ground energy state? That is E1. So here what we can say, we know that En equal to n square h square upon 8ma square. Directly you can use this formula. This just I have shown you for your remembrance. So directly we can use this. We know that the energy of any nth state, that is the eigenvalue, is given by n square h square upon 8ma square. But now you see it here. Now what is given? What will be the energy in the E2, that is the first excited state? So in the first excited state, n is equal to 2, and if you are saying n equal to 2, and here I am going to substitute n equal to 2, so it will become 4 h square upon 8ma square. I have not substituted any value, right? And this value is given equal to how much? This value is given equal to 240 electron volt. So this value is equal to how much? 240 electron volt, right? All right. Now if the same electron has jumped over to E1, right, then what will be energy? N equal to 1 I am saying. So 1 square is your 1 h square upon 8m. But now what we are saying, its width has been doubled. So here the width was a, so now that width has become 2a, and therefore a square is your 2a whole square, so it is going to be 4a square, right? So what I can do here, I can take the ratio of E2 and E1, right, and that ratio is how much? 240, right, upon E1. That will be your 240 upon E1. That is E2 is equal to how much? 240 electron volt upon E1. So just I have divided these two. This is your equation 1, this is your equation 2, this is your equation 2. So just I have divided these two equations. So E2 upon E1 is equal to how much? 240 upon E1, because this value you don't have been given, it's a E1 only. And then this equal to how much? You take this value divide this value, that is you take this value divide by this value, and you just do the simple division, right? So this value you will be getting will equal to 16, because all the rest thing will get cancelled. 8m will get cancelled, a square will get cancelled, h square will get cancelled. So finally you will be getting the value of 16, right? Then what we can say, then what will be the value of E1? So E1 will equal to your 240 divided by 16. So 240 divided by 16 will equal to how much? 15 electron volt. So this is the value that you will have in your ground energy state. This problem can be solved in other way also. What can be the other way? Here this value, you look at equation 1. In the equation 1, the value of E2 is given, right? So from, and we know this is the electron, so mass we know, what is the mass of the electron that we know, right? So substitute all those value, right, and calculate the value of A. Energy is given, right? Energy is given. So except A, everything is known to you. So find out what is the value of A. Whatever value of A you have got, double it, right, and substitute in equation number 2, right? A value you substitute over here, right, and double it. So as it is now, you can substitute, because here I have already doubled. So the value of A you just substitute in equation number 2, and then you will be getting the value of E1, and that again will be your 15 electron volt. So I think you should do it yourself, right? Try to do yourself. Same answer you will be getting. I have already tried. All right. So now let us see the next problem. Now this is the problem that I am giving you to do yourself, right? And this is a very, very easy problem. An electron is born in one-dimensional potential well of width 0.18 nanometer. So what is given? A is given. Find the energy value in electron volt in the second excited state. So second excited state does mean n equal to 3. So what is the value in n equal to 3? So what is given? Given n equal to 3. N equal to 3 for the second excited state. A is given 0.18 nanometer. So that I have converted in terms of your meter. So this equal to how much? 0.18 into 10 to power minus 9 meter. H is your Planck's constant, right? M is the mass of the electron, right? And here you have got the formula. This is your formula. Let us suppose this formula is your A. This is your equation number A. So here you substitute all those value, you will be getting your answer, right? And what will be the answer? Answer will be your 104.81 electron volt. So first you will be getting the value in the joules, convert that, that is divide that value by 1.6 into 10 to the power minus 19 coulombs, and then you will be getting in the electron volt. So this is the value that you will be getting. So now let us move to the next problem. An electron is born in one-dimensional potential well of the width 1 angstrom. So here again the width is given, but in finite wall height, of course the same thing. Find its energy value in the ground state. So ground state does mean n equal to 1, and in the first two excited state. So this again I have taken in the little different way, therefore I am going to show you. So here the A has been given to you 1 angstrom, so 1 into 10 to the minus 10 meter, and rest are your constant. Right, you have to find out the value in the ground energy state and the two excited state. So this is the formula that we have already obtained. En equal to n square h square upon 8m a square. For ground energy state, what we can say, n is equal to 1, and same formula I have applied, and you have got this much, right? So this is the value that you are getting. How much value you are getting? 6.029 into 10 to the minus 18 joules. This is the value of your E1. Now what will the value of E2? So E2 is equal to n square into E1. So this is what I have applied over here. So just you look into. So for the second excited state, n equal to 2, right? So what we can say, n square into E. Just I have shown you, it is directly proportional to n square, right? So if the first energy state is E naught, then in the second state it will be equal to 4 E naught, then the third 9 E naught, like that, right? So it is directly proportional to the square of number of the quantum energy state, right? So En is equal to n square into E1. So n square, so 2 square is equal to 4. So whatever value you have got in the ground energy state, you just multiply it by 4 n square, right? So n square is nothing here, it's a 4. So you just multiply by 4, and this is the value that you are getting. Similarly, for the second excited state, naturally n equal to 3. So 3 square is equal to how much? 9. So here I have multiplied this by 9, and you have got this value equal to 5.426 into 10 to the minus 17 joules. This you can also solve by putting the value n equal to 2, n equal to 3 in this formula. Let us go this way, equation A, and here also you can substitute n equal to 2, n equal to 3. But I think that's not required. If you have already calculated for the ground energy state, then this second energy state, third energy state, if it is being asked, you should use this concept, right? So let's move to the next problem. Now this is the problem on the Eigen function. So Eigen value, we have already seen 5 problems. Now let us see on the Eigen function. A particle is moving in one dimension box is described by a wave function. A particle moving in one dimension box is described by the wave function this. So if the particle is moving, so this is your box. In this box the particle is moving, this is your particle which is moving. So naturally with this you will have the de Broglie wave. This will be your de Broglie wave like this. So with this you will have a wave function, and this wave function is represented by psi, and the value of psi has been given how much? X root under 3, provided x lies between 0 and 1. So this is your 0, this is your 0, and this is your 1. So it does mean its width is 1, right? It is lying between 0 and 1, right? So between 0 and 1, right? And x equal and psi equal to 0 elsewhere. So in between, naturally here it is going to be 0. So then therefore it is going to be a independent particle, right? I'm sorry, the value of the psi is coming out equal to 0 outside this. That is no function is there. So because there is no particle, find the probability of finding the particle within the interval of 0 to 1 by 2. Now this width, how much you have taken? This width equal to you have taken as 1, because what is the probability that width you have been given? It is lying between 0 to 1, but the probability has been asked between 0 to 1 by 2. So this is your 0 and this is your 1 by 2. So this is your 1 by 2. So this will be your 1 by 2, right? So within this, what is the probability? That is, what is the probability of finding the particle only between these two, right? That is between 0 to half, right? Naturally, the probability should be, as it say, logically we can see, should be 50%, because half of the box the probability has been asked. But let's use the conceptually and try to solve this problem. All right. So let us see this problem. What is given? The wave function is given. So psi equal to x root under 3, and the limit has been given, right? x1 and x2, and that value is equal to between your 0 and half. Then what is the probability of finding the particle within that? How do we calculate the probability? Probability is given by I had shown you before the eigen values, right? Just after the Schrodinger wave equation, the probability is being calculated mod of psi whole square dx between the limit. Whatever the limit it has been asked to you, within that limit you have to find out. So mod of psi whole square dx within the limit. What is our limit? x1 and x2, where x1 is your 0 and x2 equal to half. And the value of the psi is given. This is your value of the psi. So this value I have to substitute it over here and integrate this, right? And then you will be getting what is the probability. So what I can say, integration of mod of psi whole square. So if I am taking whole square of this, so x square and root under 3 will become your 3, right? So this is going to be 3x. Now you integrate this. So 3 of course is constant, and x will equal to your x square by 2, right? Anyway, this I have taken whole square. So this is your x square. Here I have not integrated here. Next I have integrated. So this is your 3x square. So just I have taken whole square dx within the limit 0 to 1 by 2. So 3 is your constant. You take it out. Now here you have x square. So the integration of this will equal to x to the power 3 by 3. Now you put the limit. What is your limit? X equal to 1 by 2. So here x equal to what you have to put? 1 by 2. So 1 by 2 whole cube minus again x equal to 0 whole cube. Naturally this will be remain the same value. So how much you are saying? 1 by 2 whole cube minus 0. So 1 by 2 whole cube is equal to how much? 1/8, and this is coming to equal to 0.125, and now you see the probability is only 12.5%. It is not 50%. So between 0 to 1, that is 1 by 2, that is a half, the probability is again coming out to equal to only 12.5%. So never predict the value of the probability. All right. You should always calculate this properly. Now let's move to the next problem. Again on the your eigen function. A quantum particle is confined in one-dimensional box of width a, right, in its first excited state. What is the probability of finding the particle over an interval of a by 2 marked symmetrically at the center of the box? So before I am coming to the given value, let us see what does this problem says. A quantum particle confined to one-dimensional box of width a in first excited state. So this is your ground energy first, that is your ground energy state n1, and this is your first excited state. So where is the particle? Particle is here. Here is the particle, right? So this is equal to your n equal to 1, this is your n equal to 1, and this is your n equal to 2. So where is the particle? Particle is here. So n, the value will equal to your 2. Now you read further. What is the probability of finding the particle over an interval of a by 2? Let us suppose this width of this is your a. This width is your full width is your a, right? Particle is over here. That is in the second excited, that is n equal to 2. Here is your particle, right? So this is going to be half. This will be your a by 2. This is exactly the center. This will be your a by 2. Now what it says, what is the probability of finding the particle over an interval of a by 2 marked symmetrically at the center of the box? So from center of the box, what is the center of the box? A by 2, and from here a by 2 distance, and again from here a by 2 distance, right? So this is what you have been given. So now you divide into the 4 zones. This is your a by 4, right? This is your again another a by 4. So a by 4, this is your 3a by 4, and then this is going to give you the full width. So you have to find out within this interval. This is your interval within which you have to find out. So naturally this is going to be equal to your a by 4, this is your 1/4, and this is going to be your 3/4. This is going to be your 3/4, right? So between what you have to find out? Between what you have to find out? A4, 1/4 of the box, right? A4 to 3a by 4. This value is your 3a, 3/4, 3a by 4. Between this, what is the probability of finding the particle? This is what you have to calculate. I hope you must have understood, because what is given? Mark symmetrically at a distance of a by 2 from the center. So center is this. Center is at a distance of a by 2, and from here you have to take the distance of a by 2. Right? Again from here you have to take the distance of a by 2. Right? From here. So naturally this is going to be divided by 4 zones. So all the zones are going to equal. So this is going to be a by 4. This is going to 3a by 4. All right. So let us see now what is given. So first excited state. So naturally n equal to 2, and naturally interval is going to be a by 4 and 3a by 4. So how this interval has come, I hope you must have understood. So now let's solve this problem. Again, this is the easy problem. Right, only we have is some simple integration that we have to do. Right, so the probability is given as mod of psi whole square within the limit dx, right? And this is the probability that we have to find out. And psi, the value of the psi x, we know is given as root under 2 by a sine n pi by a into n pi by a into x. This is the derivation. This is called your eigenfunctions, and this derivation we have already done. So eigenfunction is given by, that is the value of the psi x is given by root under 2 by a sine n pi by a into x, right? So that value here I have to, this is your, let us suppose this is your equation 1, and here I have to substitute the value of your psi x. So let's substitute the value of the psi x. So what I am going to do, integration a by 4 to 3a by 4, right? And then mod of psi whole square. So this whole square I have to substitute it over here. So this is what I have taken, right? Whole square I have taken dx, right? Now you just break your whole square. So whole square has been broken. So 3a by 4, this is your integration. 2a, this is whole square you break, so square root will go over. So 2 by a, this will become your sine square, and n is equal to your 2, because it is given your first excited state. So the value I have substituted here for this value n, here I have substituted n equal to 2. So this is your 2 that has been substituted, right? And this is how you are getting this value, right? So what is left is to solve this integral. So let's solve this. Now this is your sine function, sine square. So naturally we have to convert in terms of 1 minus cos x. So we know 1 minus cos a, 2 sine square a by 2. So this is what the formula I have applied. So what we are going to do, this is being divided by, this is being multiplied by 2 and divided by this, that is here, this equation is being multiplied by 2 and is being divided by 2, so that it is getting converted in that formula. So 2 by a is your constant, 2 by a is your constant. So this I have taken out of the integration, and this has been multiplied by 1 by 2. This has been multiplied by 1 by 2 and divided by also 1 by 2, and therefore it has become sine 2a, and then 2 sine a, and then we have taken 1 minus cos a, 2 sine square a by 2, right? Sine square is already there, so 2 sine square a by 2, right? And this is what I have, the formula has been taken. So I'm going to this I'm going to integrate this, right? So again this a by 2 has also been taken out of the integration, and 2 by a is already there, right? Then this is your dx, this is your 1 into dx. So this is your dx, the integration of that is going to be your x, and then here this is your the cos. So integration of this is going to be sine. This is your cos, and integration of this is going to be sine, and we have to divide by this coefficient. This is your coefficient. So this is what has been done, right? So here you have, I have divided by the coefficient. This is the coefficient with which it has been divided, right? It is your 4 pi x by a. So as you can say, a has gone up, right? This is why it is in the multiplication. and the integration of the cos is sine, that has been taken, and then you just substitute the limit. So now what you require to do is just you have to substitute the value of limit. Here I have shown it, here all these steps I have shown it, but it was not required to show it. Why? Here you can see this is coming in the order of sine n pi. This will be coming in the order of sine n pi, and sine n pi will always be 0. Here as you see, after solving you are getting sine 3 pi. This is also coming sine pi, right? So that is coming in the order of sine n pi, and sine n pi will always be 0. So what is required? Now here you substitute your upper limit and lower limit. So this is what I have been done. Here also it has been solved properly, right? And the limits has been substituted. In this again, as you can see, the limit has been substituted, and by substituting the limit, I will recommend that you do yourself with properly with your pen and pencil. So then you are going to get this value will equal to your 1 by 2. So here you are getting a, and this a will get cancelled, right? 1 by 2, 0 minus 0, because this value will be coming to be 0. So this you are getting as 0.5. 0.5 is nothing, it's a 50%. So the probability will remain 50% within the box. So in this way, all the types of the problem I have completed in the quantum mechanics, right? We had started from the de Broglie concept on the Heisenberg uncertainty concept. So 2 separate class of the numerical problem we have done, then the eigenvalue and eigenfunction. So all the types of problem have been taken care. So only it's recommended that you should do all this problem sincerely with your pen and pencil, and if there is any problem you can always come back, right? Thank you very much.